Hey, hey, hey! It's section 2.1. We're starting chapter 2, which is all about proofs, reasoning and proofs. So we're going to start off section 1 talking about what inductive reasoning is. So, well, let's jump right in. Here's the goal. It is to use inductive reasoning to make conjectures. So there we go. Um, we have a couple of vocabulary terms we're going to start off with right away. Because they kind of deal directly with what we're doing today. And the first one is simply inductive reasoning. What is it? Inductive versus deductive reasoning. Today we're talking about inductive. Inductive reasoning is reasoning based off of observed patterns. So if you see patterns, you can kind of make a guess as to what's going to happen after that pattern. And that guess is called a conjecture. It's a conclusion you reach using inductive reasoning. So it's essentially your educated guess. And then finally, a counterexample. We're talking about counterexamples, how we can find counterexamples. It's an example that shows a conjecture is incorrect. All right? So those are the three key terms for today. Now we're going to go into a little bit about how to use inductive reasoning. And for some, it might come easily. For some, it might not. But we're just looking for patterns. So patterns, patterns. There's so many patterns in math. That's why I think that this should come easy for most people in math, but maybe it won't. So looking at problem 2, it says using inductive reasoning. Look at the circles to the right. What conjecture can you make about the number of regions 20 diameters form? So I'm going to put the diameters on the top. I'm going to put the regions on the bottom, just so we can. There's one diameter here that makes 2 regions. Now we have 2 diameters. That makes 4 regions. Now we have 1, 2, 3 diameters, and we have 1, 2, 3, 4, 5, 6 regions. Well, if you look at the patterns, it looks to me like every time you have, depending on how many diameters you have, it gives you twice as many regions. And that makes sense, right? Because a diameter cuts something in half, so it makes something go into 2 parts. So my guess, my conjecture would be 40 regions. And that's using inductive reasoning. I'm looking at patterns and I'm making a conclusion. I'm making a conjecture. So here's some more examples. You can pause it and try them on your own if you'd like. But I'll go through a couple. I'll go through them as well. So trying to figure out what the patterns are. Number 1 says 3, 6, 9, 12, 15. Hopefully you figured out after that. It's just going up by 3s. So multiples of 3, so we have 18, 21, 24, and so forth. So let's look at number 2. So it's 9, then 3, then 1, then 1/3, then 1/9. Now maybe you can tell that each time it's being cut in thirds, or multiplied by 1/3, or divided by 3. So we're going to do this multiplying by 1/3 thing. So if we multiply each by 1/3, it works so far. If we multiply 1/9 by 1/3, you get 1/27th. Do that again, you get 1/81st. And you do that again, you get 243, I think, and so forth. So it's just getting smaller and smaller and smaller. Now number 3 has to do with the letters. So we have A, C, E, G, I, K, M. Let's see, A, B is left out. C, D is left out. E, F is left. I think it's every other. So if I'm looking at the pattern of every other, we have K, J, K, L, M, N is left out. O, no P, so Q, no R, so S, no T, so U, and so forth. So again, patterns. We're just making conjectures based off of patterns. This is one of the greatest tools that we have in life because there's so many patterns that we see in math and in life in general, and we can utilize inductive reasoning to, make conjectures about things. All right, let's look at this. It says make sure you have enough information before you make a conjecture. Otherwise, your conjecture may not be accurate. So if you can't like actually tell that there is a pattern, then don't try to make a conjecture. Otherwise, chances are it might not be accurate. So looking at number 4, it says sales of backpacks at a nationwide company decreased over a period of 6 consecutive months. If you look at it, this would be November, December, January, February, March, April, and May. So they're gradually decreasing at a pretty steady rate. What conjecture can you make about the number of backpacks the company will sell in May? Well, my guess is it's going to keep going in this same pattern. It's going to go still down here. It's going to be down to like 8,000. And it's going to go down here. And that's not zero, by the way. This little symbol, in case you weren't sure, that just means that we're skipping from 8,000 to 0. So it's just it's skipping out on all those parts, so you don't have to show it. But really, it would keep going down by 500 like it is. So it would be down to 7,500. Um, that's what it says for A. What conjecture can you make about backpacks and Junes? It might keep going down. But look at letter C. Whoops. Or sorry, not letter C. Oh, things are going crazy here. Come on. All right. Well, anyway, letter B says, is it reasonable to use this graph to make a conjecture about sales in August or even September? And explain. Reasonable, I would say it seems right that the pattern would keep going, but think about think about what happens in August and June. School's about to start. That's when people start buying more backpacks. So I'm going to say for this one, it is not reasonable. You need to look at other factors. This is not one where we could use that to make a prediction. Now we could use sales for years at a time and see like, oh, it's pretty consistently at this amount in May. Okay, and then we can make conjectures off of that. But just looking at this one set of a few months in a row, that's not enough information to give us the rest of the year. Okay, so be careful with that. All right, second part of this lesson is counterexamples. And we're looking at what a counterexample is. So if you remember from the beginning, a counterexample is an example that shows a conjecture is incorrect. So we're going to do stuff with counterexamples. Um, Examples. Find one counterexample to show that each conjecture is false. All you need is one counterexample, one example that would cause it to be false. So number one, all vehicles on the highway have exactly 4 wheels. Well, how about a semi? There's a counterexample. Or a motorcycle. There's another one. So those don't have exactly 4 wheels. So there's one counterexample, so that statement is not always true. All plurals end with the letter S. So let's think of a plural. How about geese, or children, or um, moose? So they don't always end with the letter S because there are some plurals that do not. So there's one example. Number 3, all numbers are divisible by 3 that are divisible by 3 are also divisible by 6. Well, I'm going to take the easiest one. I'm going to say 3. 3 is divisible by 3 because you get 1, but it's not divisible by 6 because you'd end up getting a fraction. There you go. All right, and finally, all prime numbers are odd integers. So prime number, well, 2. There you go. 2 is the first prime number. We have 2, 3, 5, 9, no, not 9, 7, 11. They're pretty much all odd except for the first one. So those are counterexamples. Finding some example that shows that the conjecture, that educated guess or statement is correct. All right. So we're going to end it with one closing question I want you to think about. As if one counterexample can prove a conjecture false, because really you only need one and the conjecture is false, how many examples do you think can prove a conjecture true? There's something to think about. And think about that as you go back and also think about the goal for today, which actually had nothing to do with counterexamples really, but it does have to do with conjectures. And it's using inductive reasoning to make conjectures. That's all for section 2.1 on inductive reasoning. I hope you enjoyed it. I hope you learned something. And we'll see you next time.